called Industrial Data and the Resurrection of Ontologies. So as I think everybody knows, industry is transitioning from document-based manual work processes to more automated work processes supported by computers. And to achieve this, a common digital language is needed that can be understood by both machines and humans. And this includes grammar and vocabulary. So people have been working with ontologies to achieve this goal for decades, absolute decades, with very few examples of success. But there have been some. Notably, the gene ontology is widely used in bioinformatics, and FIBO, the financial industry business ontology, is widely used in finance. However, paradoxically, the arrival of large language models, which we've all heard about, ChatGPT and the like, has ignited interest in what is possible with enterprise industrial data. In other words, the data owned by industry and governments and organizations like UWA, and paradoxically resurrected an interest in ontologies, and I'll explain why. Oh, there's something wrong with my slide. Hold on a minute, sorry, something up with my slides. It's not showing this bottom slide. Okay, there we go, sorry. Okay, so ontologies assist in the development of common digital vocabularies within and across organizations that are required to share information such as material master data, asset design data, product manufacturing and maintenance data. And they are also used for reasoning. Think of this as logically checking facts and engineering assertions. So this slide shows on the top different phases of an asset facility life cycle. Conceptual design, construction operations go from left to right, and broadly similar phases apply in engineering product design. At each stage of the life cycle, there are different groups within an organization and many companies outside of the organization, such as engineering consultants, parts and suppliers, and contractors who need to use and add to design information. However, for the last 100 years, when information is transferred within and between these groups, it's done so manually in the form currently of PDFs and data files. So one vision for the engineering community is that in future, we'll be able to exchange information models, as kind of shown in those colored blocks at the bottom, as shown, and these information models are created by different stakeholders in the life cycle, but they use a consistent machine readable format. And as such, they can be continuously checked for design flaws through automated work processes. Furthermore, the fragments of information now represented through several information models can be integrated along the way in an easy way to ensure consistent design and a valid description of the facility. And eventually, this will form the basis of the much vaulted digital twin shown in the right-hand corner. This model of models captures not only the historical context and design decisions, which are so important in the operational phase, but also very important to maintenance engineers like me, who are trying to prevent failure in operations, and those failures often go back to decisions made in design. You only really have to think of the latest Titanic exploration disaster that we had with materials design, of the importance of understanding design decisions. So this vision of shared information models across the life cycle is currently being realized in the Norwegian offshore community. Equinor, which is the Norwegian government operator of offshore facilities, has specified some years ago the use of a common data model for use in design. The structure of the model used is public, and it's based on W3C web standards, supplemented by ISO International Standards Organization engineering standards, such as 1596 and 81346. And as you can see in this diagram, you've got the operator on the left. They pass the data models through APIs to their suppliers like Aker Solutions and Technip. They work on it using their own proprietary models, but all the data that's generated and the information that's stored is done so in a common, using a common information framework. So is this an example of a 20-year journey to overnight success? Well, maybe. I want to give you a little bit of historical context and how we have got to where we are today with the Norwegians. So the weirdly named Post-Caesar Association, I still don't know why it's called that. PCA was formed in Norway in the 1990s, and it's a non-profit global standardization member organization promoting the development of open standards-based specification for the energy industry. The Norwegian industry and the Norwegian government got behind this, and something we dream of in Australia, a consecutive series of government and industry funded projects shown in blue there has followed from 2006 to 2017. The most significant of these were the European $13 million Optique project in 2012, followed by the Ready JIP in 2017. The result of this is a significant number of tools and demonstration projects and a continuous and growing industry stakeholder and researcher base. They have never been without funding. In 2018, the ISO 15926 Part 14, what currently just called Part 14, a technical report ontology was published. And this is a very important step, and it's the basis of the industrial data ontology that is the title of my talk, and I'll talk more about this later. So Norway and its Northern European colleagues were not alone in their interest in ontologies. Across the Atlantic, the election of Donald Trump in 2018 and the Make America Great Again campaign led to a really significant increase in funds for US manufacturing. So one of the key initiatives of this was that the National Research Agency in the US, NIST, was charged with improving interoperability in the US manufacturing supply chain, and hence formed a group called the Industrial Ontology Foundry. So it's worth noting that Caitlin, sitting there in the back, and I have been deeply involved in the Industrial Ontology Foundry, and we lead the Global Maintenance Ontology Working Group for this. And in 2019, I was the co-organizer, and in fact, Tom Smoker and Caitlin were able assistants in the early journeys of their PhDs of a workshop in Oslo that brought the American Industrial Ontologies Group and the European PCA groups together for the first time. And it was really at that was a bit of a tipping point in 2019, because we had people from 43 companies turn up to a meeting about ontologies in Norway in February. And they all paid their own way. So we knew that there was serious interest, because nobody goes to Oslo in February unless they have to. So at this point, we really felt that things were beginning to move. In 2020, a related but bigger European group managed to get €4 million from the big European Horizon 2020 project for something called OntoCommons. Unsurprisingly, this is dedicated to the standardization of data documentation across domains relating to materials and manufacturing. While, in my opinion, it's more university and research driven, it has focused a lot on developing usable demonstrators and toolkits, such as an ontology register for cataloging domain ontologies. As we know, many of you from the engineering world will know that standards in engineering are a vital part of our work. And despite its widespread use in Norway, the ISO 15926 Part 14 document produced in 2018 had not, as of the start of this year, been formally adopted by ISO. And as a result, it's not so easy for companies to use it, because they really want the ISO certification. So to accelerate this in 2020, a joint industry project was funded, largely out of Norway, to prepare the ISO submission. And the partners included Equinor, some big names, Siemens, DMV, Abel Grundfos, Total Energies, the big French giant oil and gas company, and two universities, the University of Oslo, and would you believe it, the University of Western Australia. So I spent a large part of my sabbatical, which started in January, working on this ISO submission that was made last month and approved in June. So the orange dots here show the activities that I and to a large extent Caitlin have been involved in with this since 2019. So what does an industrial data ontology look like? It's not very exciting. I do apologize for the small print, but essentially it's a model. In this case, it's what we call an upper ontology. It's very abstract. It's like all good things mathematically and in computer science. It's a useful abstraction, but it's an abstraction nonetheless. But its value is that it represents a wide range of concepts that allow us to model things of interest in the domain. And as it says here, it supports the building of vocabularies and the development of asset models that can be used as reference data libraries. And very importantly, this particular one exploits something called OWL reasoning, which is a non-trivial thing to do. And the OWL reasoning enables a number of automated processes, very important in quality control. I realize this all seems a bit abstract. So I thought I would try and make it a bit grounded a bit by using an example of an ontology that you may unwittingly have used if you have ever used the IKEA catalogue. So the IKEA catalogue, if you've ever shopped online with IKEA, they got rid of their paper catalogue some years ago, and they produce only an online version, and it's built on a knowledge graph with a very solid product ontology behind it. And within the IKEA enterprise, this ontology is owned by a central ontology team that controls it. And it has allowed for the development of a number of decentralized controlled vocabularies aligned to this top ontology that are developed and managed within the business. For anybody interested in this, there are some incredibly engaging talks on the IKEA ontology. Strangely enough, they're podcasts very fun to listen to by their chief ontologist, Katerina Carey, and there are some links on the bottom here if you want to find that, and explaining how, unlike Amazon and other groups that provide recommendation systems that are based on the wisdom of the crowd, you're going to buy that. We suggest you buy this because other people have bought this. The combinations and recommendation systems come from the ontology and are curated by the interior decorators. So there is domain and IKEA knowledge built into those recommendations, not just based on what people have said before, which is an important development. So one of the early examples of the successful deployment for industrial ontologies was made early in the development of the Johan Sverdrup drilling platform. And so this was required by Equinor to have this ontologically consistent material master data. So they paid for the development of the material master data, and they ensured that the designers used that in order to model piping and valves worth over $60 million using a set of modular ontologies aligned to Part 14. And I draw your, this is a busy slide, but I draw your attention to the benefits shown in the grey box on the right. They reported very significant cost reductions, improved quality control, and also productivity gains through the ability to reuse modules of the ontology when they did follow-up design projects. So why my interest, as many of you know, I'm a maintenance engineer, and so this would seem to be a long way away from my real work. And while I would love to access design data, unfortunately, many of the assets that I work with, you know, from the mining industry were built in the 60s and 70s. So the design data is long gone. And the data that I have to deal with now largely comes from unstructured text. And there is absolutely masses of this in organizations today. And so I'm very interested in how we make this machine readable and how to reason over using computers. And I believe that these tools that are coming out of the design and the requirements end will work equally well on through life support data. So fortunately, we have access to some really talented groups, specifically the NLP-TLP group at UWA, and of course the wonderful Theme 1 group here in the center for transforming maintenance through data science, and also students who have been funded from the System Health Lab. And for the last 4 years, members of these teams have been developing pipelines to extract information from maintenance text, such as maintenance work orders. If you look up in the top left-hand corner, that's a typical order. They're a bit like doctor's records, but for equipment, and other types of text like procedures and condition monitoring reports. One of our key competitive advantages is the formation of these meaningful triples through collaborative annotation and the use of ontologically sensible entities when we choose the schemas. And you'll see from the color coding here that when we identify nodes, the round little bubbles, and relations, we provide them with class and object properties such as physical object or activity, and these are mappable to 15926 Part 14. For those who haven't seen this work before, some of the things these annotated texts enable us to do are that we can, for example, transform the text in the blue box on the left which is a long text of a maintenance work order, into a causal tree on the right. And each of these nodes has a color, blue for item, pink for undesirable state, that can be used for querying and, if needed, for reasoning, so that we can start to really understand, in this particular case, from all of that mess of data on the left, that we have a shaft collar that's slipped down. It's caused the ram to bend, which is called the striker to misalign, which is called the burner to fault. And we'll be able to extract this at scale from many thousands of work orders. Caitlin's PhD thesis is extending the boundary of how ontologies can assist maintenance professionals in other ways. In this slide, which is from a paper published in the Applied Ontology journal, which is very prestigious and maybe not as applied as we thought it was going to be, because it's a very applied paper for them. Caitlin showed how to address some real questions maintenance personnel have shown here in the text in the middle about the procedures that are stored in their computing systems. These questions can be answered using Sparkle queries that support the ontology's reasoning ability. Of particular note here, one of the things that is really very pragmatic about ontologies is the idea that in this particular case, Caitlin used the foundational part 14 ontology. You can see that in the top left. She was able to reuse other ontologies that already exist, like the time and an information artifact and a relations ontology, and then make one small ontology of her own. And this idea of reusing building blocks, because you have a common data model and common ontological commitments, is at the heart of what makes ontologies so one of the things that makes them really powerful. And providing you can control and you have a shared use of these ontologies. So part of this talk is a requirement of my sabbatical. So the question, what did I do on my sabbatical? So I spent most of my time in Denmark and Norway, shown in the orange dots here, working on this submission of what's called the industrial data ontology to ISO. A major part for me was the collaboration with two companies, Grundfos, an international pump company, and Siemens, an international electronics company, on a use case for this particular submission. This developed and described an ontology for automatic verification for an Internet of Things device. And I'm delighted to say that that when we came to the IDO submission, that UWA is listed as you can see there with those other partners as one of the core contributors for the industrial data ontology. I also managed, in the top right, to spend some time with the Ontocommons group, which happens to be in the south of France, which was a real hardship posting, and see what they're doing. And then finally, which was a lot of work, I managed to attend this 5-day meeting in Paris, though I attended it from Australia, which wasn't really so much fun, and a lot of very late nights. So one of the questions that comes up every time I mention ontologies to software engineers, as soon as you step outside of the friendly world of ontologists working on this, and I deal with people who work for real companies and have software engineering and architecture backgrounds, people always say, why do we need them? And how would they fit into the way we do business nowadays, and so on. So I think that there is a real issue for the gap between the ontology work that I and others are doing and want to use in the business, and the schemas we want to develop and the tools, compared to what enterprise architects have and control and can and can't be run on enterprise IT systems. So with a bit of trepidation, I'm going to share with you some ideas about risk management to bridge this gap. I'm really putting myself out here now. Okay, so when I think about enterprise systems that I have used in my time as a reliability engineer, they largely include the blue box on the left-hand side. So by putting it inside a solid blue box, I'm indicating these things exist inside the enterprise that I either work for or with. And they include SAP, many of us know SAP. This is an enterprise resource system, various software in the MES or manufacturing execution systems, such as computerized maintenance management systems, project scheduling, purchasing. When I want operational data, such as tonnage data, I'd go to SCADA. And a long time ago, when I was in process engineering, I would do things in ladder logic on the PLC, and I would be collecting data straight from the sensors to the SCADA system. So in the main, everything shown in that blue box on the left in that purple diagram are based on relational databases. Relational databases are tightly controlled by the enterprise IT groups. They get to choose the naming conventions used. And it's worth saying that in 30 years and being inside many organizations, I've never, ever seen anything consistently applied. So for an example, a piece of equipment in one system will be called Equip ID. In another system, it will be called Asset ID. In another system, it will be called Functional Location. So data wrangling for analytics purposes is and continues to be a complete nightmare for users. In addition to this, shown in the bottom is a dotted line. And this is all the people like myself who worked for the enterprise that did things and developed things beyond the remit of enterprise IT systems. We have our own laptops. We created hundreds of thousands of documents, data, models, using all manners of software. We know where they are on our laptops. And these documents have for years moved in and out of the organization with very little security. However, and we move to the middle of the diagram here, all this changed dramatically about 5 years ago with the advent of cloud storage and increasing concerns about enterprise security and confidentiality. As I'm sure we all know in here who work with industry, if you work on St. George's Terrace now, no longer can you plug a USB drive into your laptop or easily attach files to an email. Here at UWA, soon we will all be migrating files from our H drives to the cloud. All this provides much greater control for the enterprise, and they can control what we do with it. And in many cases, organizations are putting all of this data into what used to be called a data lake, but is now increasingly being considered a data swamp. So in these data lake swamps, there are no consistent schemas. There no use of agreed classes and relations, like I discussed earlier. There are no sensible tags, and really nobody can find anything at all. So as a result of not being able to find anything, what our enterprise is doing. And if we move to the bottom right, you'll see that I note that they're spending vast sums of money on third-party organizations to develop company-specific solutions to index and find data. And these solutions, I note, are bespoke. They're not general, they're not based on generally accepted schemas. They're based on data models that are specific for the company and therefore involve a huge risk of vendor lock-in. And you also, when you do this, need to develop sensible schemas. And many organizations are getting involved with groups like Snowflake and Colibra and others like that. So let's jump sideways a bit and ask ourselves, have we been there before? There are some in here who will remember the early days of the internet, some who were probably deeply involved in it. But just to remind those that didn't, we had lots of different groups, each developing resources and data that needed to be made findable. So how was this achieved? Did the internet form a large IT department and a big bespoke solution? No, it took a community, the World Wide Web Consortium in 1994, to develop standards and guidelines that everybody has since adhered to. Specifically of interest here, as noted, are the standardized semantic web stack technologies, including the RDF framework, OWL, Sparkle, URIs, XML, and resources such as schema.org. We take for granted that we can find data anywhere on the web because we have this invisible substructure and network in place. So more and more people are asking, what about using web concepts on enterprise data? And I'm sure there are some people in the room who will think this is completely daft, but not knowing any better from my position, it does seem as though this is an attractive idea. Can we leave our enterprise data where it belongs in the data sources or the cloud or wherever it is? Can we index what we need to using W3 standards? Can we extract to knowledge graphs as shown here? And build these knowledge graphs using open source and shared ontologies as shown up in the top to form a semantic layer that can then be used to support a variety of business outcomes. For this to become a reality, we need enterprise relevant ontologies, and for engineering, we need an industrial data ontology. We know we can do asset information model exchange. The work in Norway I shared earlier has demonstrated this, but we need to be able to link this engineering ontology work to the wider business like this under the jurisdiction of enterprise architects to allow us to scale more broadly over the organization and across the engineering community. And I would say I didn't make this figure, so it's possible to start seeing these figures come out. More people are talking about this now, whether people will think they're mad or not. But nevertheless, I do think this is a home for ontologies. To show how fast things are moving, I'll go back to the other slide. To show how fast things are moving, this morning I was asked by Total Energies, based in France, if UWA would participate with the Chifos group, which is a big group involving all the companies on the right, on a new program of work on semantic modeling. So, and this is for capital facilities handover specification. So there are groups who are beginning to really talk about this in the industrial way. Just go back to this. So this is my idea that we will need to resurrect ontologies and so that we can use them for this semantic data layer alongside other web ideas. But the biggest problem is, I think, is who will develop this. So I had a look at some data here, and you know, how many enterprise ontologists do you know? And the picture is not good. I have a reasonable network into the business community through LinkedIn. And it's big enough that when I made a post about Caitlin's recent paper on digitization of ontology procedures, something you would think not many people would get excited about, that I did get 7,500 impressions. So I have a reasonable wide network. And then if I use that network and I hop out 3 hops in the graph to someone who knows someone who knows someone who's connected to me, then I find 10 ontologists in Australia. That's not many. If I do the same thing in Denmark and Norway, they only have together 10 million people. I find 156. I looked for, but I couldn't find any units in computer science and software engineering schools in Australia teaching ontologies in the semantic web. Yes, there are units in linguistics and social sciences and logic and philosophy, and promisingly one on health ontologies in the University of Tasmanian Business School, but none otherwise. The recruitment site Seek doesn't recognize the term ontology or ontologist as a keyword, but the site Indeed has 10 ads in Australia as of yesterday retiring ontology skills specifically in their requirements, and there are over 500 open right now in the US, many of them with well-known companies that you see there, Tesla, IBM, Toyota, and lots of banks. So I conclude that things are changing fast elsewhere, but maybe not in Australia. So in concluding, I think ontologies, I would like to think that they're having a resurgence with this interest in enterprise semantic web data. There's certainly an interest from the community, in the design community of the more sophisticated engineering design offshore facilities. And I'm hoping that that will spread slowly into other sectors. I'd like to thank a lot of people, the groups listed here and all who are part of those teams. Special thanks to Wei and Tim, Caitlin and Tyler and Michael, without whom I couldn't do any of this work. And finally, also a shout out to my head of school and head of department who signed the paperwork to allow me to take my sabbatical. The past 6 months has been really fantastic. I've learned masses. I continue to learn a lot, and it's opening lots of new doors. Thank you very much.